Hi everyone, and welcome to another episode of Mr. Carlson's Lab. So this last restoration I've been working on has taken an extremely long time, and I'm still working on it. So since this is taking so long, I'll share another Patreon video with you guys. This is another one of the Troubleshooter series videos, and in this video I show you guys how not to destroy a hybrid style amplifier, and there's a whole bunch of other little tips and tricks in there as well. Again, the whole idea of this Patreon site and the Patreon series is to share my skill set with you guys so that you can repair, you can restore, and you can even design electronic equipment with ease. At any rate, this video is going to show you how not to probe around in a piece of electronic gear that has hybrid technology. You can very, very innocently go from one area of this amplifier to the next and completely destroy the solid state end of things just with a probe, and you'd never suspect why. It's a little trap that hides in troubleshooting. And I'm going to share that with you in this video. I call that a little golden nugget, and these are very, very important things to remember, especially if you're going to be troubleshooting any kind of mixed technology, any type of hybrid style technology. So there's a lot of really good information in this video. I also share a lot of my thought process as I'm going through this video. So let's get started. In the last Super Electronics Troubleshooter video, we took a look at a Fender Twin Reverb guitar amplifier. Now that was all vacuum tube technology. It was a 135 watt vacuum tube amplifier, so lots of high voltage and high current available inside that amplifier. So the next step is to take a look at hybrid technology. This amplifier that you're looking at right here is a mixture of solid state and vacuum tube technology. Now, they're making these things nowadays, except nowadays they're a lot more complex. This design here is from the early 80s, and it's a nice design to take a look at. This is a nice simple design. As we go along, we'll get into the more complex design with the microprocessors and things like that. But there are a lot of very important lessons to be learned by looking inside this amplifier and knowing how to troubleshoot and how to probe things. You can very badly damage this amplifier just by probing around inside it. So just by using your oscilloscope, you can pretty much destroy the ICs in this amp. And I'm going to show you this little catch that gets a lot of technicians. So what ends up happening is one of these amplifiers, or even one of the modern ones, will come in dead. All right, so the amplifier doesn't do anything. The fellow that's working on the hybrid technology, so the vacuum tube and solid state technology, starts probing around and looking for signals at the vacuum tubes, and then we'll start troubleshooting the rest of the circuitry as well, not realizing that as he's troubleshooting the rest of the circuitry, he's blowing it up as he's going along. So the amplifier is silent when you start, and it's just getting more and more silent, and these techs are creating more and more damage as they're going along because of one very simple rule. And I'm going to share this little tip with you guys. This is very important to remember. This is one of those little golden nuggets that you really need to remember whenever you're working on any type of a hybrid or crossover technology like these types of amplifiers. And it's very common today. A lot of vacuum tube amplifiers are in production that have a mixture of solid state and the glass technology inside them. So one wrong move and these things are finished, or you're just creating a lot more work for yourself. So the story on this Legend amplifier is that it's cutting in and out. It's intermittent and the controls are very scratchy. So what we're going to do is we're going to go inside this thing and we're going to address the problems that need to be addressed. Now this is one of those amplifiers that's basically get the thing up and running. There isn't going to be a massive capacitor swap out unless it's absolutely needed. The instructions were to replace what needs to be replaced and make the amplifier work so he can play with it. It's just basically his hobby amplifier. Supposedly these Legend amplifiers have got quite the history behind them. So I'll let you guys research that if you're interested in looking up the history behind this Legend amplifier. At any rate, so what I'm going to do is I'm going to take this thing out of the case now. So there's not a whole lot to take out of this thing. It's a little simpler to get apart than the last one. So in behind here, There's just a couple of screws that need to be removed and a few jacks that need to be pulled out. I'm going to save you from all of that because it's really quite simple. And what I'm going to do is get the amplifier itself up onto the bench, and we'll take a look at the top side and the bottom side like we did before. I'll show you how to effectively troubleshoot these amplifiers, and I'll show you how to very quickly troubleshoot solid state stuff without schematics as well. Now, I've looked online to try and find a schematic for this particular Legend amplifier, and it just seems to be at this point unobtainium. But you know what? This gives us the perfect chance to go in here and just follow the signal along. And I'll show you a few hints and tricks with the solid state devices in order to get you through this stuff very, very quickly. It really is quite simple. And once you see how easy it is, just like in the last video with a Fender amplifier, you're just going to go, oh wow, it really is quite simple to troubleshoot. So I'll get this thing onto the bench and we'll get started. This is a topside chassis view of the Legend amplifier, and as you can see, there's really not a whole lot to look at on this thing. It's nowhere near as exciting as a vacuum tube amp. So you can see on the top side here, we have two TO3 package transistors. So these are obviously going to be the output transistors, and this is going to drive the speaker. They put nice little insulating caps on the actual transistor cases so that you can't run a screwdriver down and short anything out, but they did leave little holes in the top so you can put your probe down through that hole and measure the case of the transistor, which is kind of handy. That can be done from the top side here, and as you can see, it looks like we have two other test points here that you would have to be very, very careful because you could very easily short this to the case or to the actual chassis. We have two preamplifier tubes, and that's all we have on the chassis here. There's no other vacuum tubes. So you can really get an idea of what Legend was thinking when they designed this amplifier. Again, all of these chassis and everything, they tell a story just by looking at their design. So we have two preamplifier tubes in the front end, and we have a solid state power amplifier section that drives the speaker. So we can very softly, or very comfortably, drive the two preamplifier sections into distortion, but if we drive the output section into distortion, it's going to be a really hard sounding distortion because this is a solid state section. Vacuum tube outputs drive into distortion and they kind of provide a smooth distortion, whereas transistor outputs or any type of solid state output, when they start getting driven into distortion, it starts to sound really, really harsh. So these are, transistors are low impedance devices, or lower impedance devices, I should say, and vacuum tubes are very high impedance devices. And in guitar amplifiers that have an output stage that has a really large transformer like that Fender, the vacuum tubes in the output stage, which were those 4 6L6s that we looked at in the last video, those have to drive a transformer, and that transformer basically has to, you can look at it like this, it transforms the impedance down to what the speaker's impedance is. So it'll take the high plate, the actual plate resistance or plate impedance of the vacuum tubes, and transfer that down to 8 ohms so that it can comfortably drive an 8 ohm speaker. So basically the transformer is doing what it's doing. It's transforming impedances. Transistors have the ability to drive the speaker almost directly, right? Because these are a low impedance device. Speaker is a low impedance device. You don't need that transformer anymore, and that's why you don't see an audio output transformer on this chassis. And in many transistor amplifiers, you don't see an output transformer at all because, the impedances are just fine. They're very close, and they can, these two transistors are very comfortably drive an 8 ohm impedance. Now, these are very close to the speaker's impedance, and this is a solid state device. Whenever you have solid state devices driving any type of speaker, if you want to drive these things into distortion, they really start to sound rough. Now, this amplifier was in production in the early 80s era. And what kind of music was really pronounced in the 80s? And if you looked up the history on this amplifier and who used these amplifiers, you'll get an idea of basically their target audience. So you can really tell that this particular amplifier was designed to play rock and roll. right? So you can really get that grunge out of your guitar with this thing. You drive these things into distortion and they're going to sound really messy, right? And then of course you have the vacuum tube distortion in the front, so you can get that soft distortion and you can kind of mix it with this really harsh distortion that these two output transistors are going to create here, and you've got your really harsh rock and roll sound coming out of your guitar if you want any kind of distortion. And on the other hand, this thing can be incredibly clean if it's just kept down. So transistors, these two transistors, as long as they're, not into their distortion region, and these two tubes aren't driven into distortion, you can really get that clean sound. So again, guitar amplifier guys, the distortion that they're looking for comes from the output stage. So basically what they're doing is they're driving the output transformer and that whole, stage into heavy distortion. And that's the reason that they sell these output attenuators. So a lot of vacuum tube audio guys, the guys that like these amplifiers, but the all vacuum tube version like the Fender Twin Reverb, what they'll do is they'll buy a thing called a dummy load. And the dummy load will have taps on it. And what they'll do is they'll crank that amplifier way up. So say that 135 watt amplifier is at say 130 watts. They'll have a big resistor that will take all of that power, and there'll be a bunch of small taps on that resistor really close to the ground end. And what they'll do is they'll take that off and they'll power up a small speaker with it. So you're missing one type of distortion by doing that. The speaker itself, when it's driven into distortion, has its own unique sound. Eliminating that sound, you still get the output section distortion because it's, driving into that dummy load, and you're just taking a very small amount of power off to drive a speaker at a comfortable room level. So basically you've got this resistor that's glowing hot inside of a box, sometimes even with a fan, depending on the kind of power that you're, causing that resistor to have to deal with. And, on the other end, there's just a little tiny speaker, then you can play at a normal room level, but get that distortion. So lots of people make these boxes. Now, this device here has that ability to, run super clean like a vacuum tube amplifier, or if you want that soft type of distortion from the output stage, you are not going to get it from this thing. You're going to get a really harsh type of distortion. So if you really like to play your electric guitar loud and you really like that distortion, this is the amplifier. This is the type of sound that you're looking for that really, really harsh sound. Anyways, I hope that clarifies up a little bit between the output sections of a vacuum tube and a transistor amplifier. If you have any more questions about the differences in the output section, or if you would like me to touch on a topic that has to deal with this in a later episode, we still have lots and lots of different types of amplifiers we're going to go over together. Leave it in the comments below, and I'll read your comment and I'll add it in. Now, there is a patron that asked a question about coupling on an oscilloscope here, and I'm going to cover that as well. So we're going to talk about AC and DC coupling in this episode as well. So I'll get the chassis flipped over and we'll take a look at the underside and see if we can spot any problems. Here we are looking at the underside of the chassis at the business end of things, and as you can see, the designers at Legend did a pretty nice job in putting this amplifier together. You can really see what the engineers and the designers were thinking just by looking at their design. I can tell you this, a lot of care was taken when this thing was put together. You can see that all the AC lines are twisted together, so all the AC lines that come out of the transformer, even the line to the fuse is twisted. That's rule number one whenever you're designing any type of an amplifier. If you have long runs of AC line that are carrying any type of current, you want to keep those twisted together. Even if they're carrying very low current, you want to either have them tucked close to the chassis or twisted. And as you can see, they're doing that all over the place here. So the thought was there, and the lines that aren't twisted together are shielded pieces of coax. They've used zap straps here to tie or loom the wires together. Did a nice job there. Now, you can see either for warranty reasons or the engineers were just really thinking ahead. What they've done is they've installed a temperature sensor on the chassis right here. So if one of these output transistors shorts out, these output transistors are using the chassis itself as a heat sink surface. So the cases of the transistors have to transfer their heat somewhere, and they're using the actual case of the amplifier to do that. So if this transistor shorts out and gets really, really hot, this temperature sensor is going to see that, and the little bimetal strip inside here is basically going to shut the amplifier off. So these are the same kind of sensors that you find inside of coffee makers and things like that. Nice thing about this sensor is it automatically resets. Downside to that, if the transistor is shorted and it's sitting in a room left alone for a while, this is going to be turning on and off. As the transistor gets hot, heats the chassis up, this will shut off. Of course, it shuts the power off, transistor cools off, chassis cools off, this thing turns back on. You know, the shorted out transistor heats up again, chassis heats up, shuts off, so you can see it'll cycle until something else burns out or until basically you shut it off. So at any rate, a little bit of forward thinking here, that's nice to see. Nowadays, you usually don't see things like this unless it's a pretty high-end design. So that's nice. Vacuum tubes over here, this is vacuum tube preamp stage. Now, one of the real common complaints in these amplifiers, and pretty much all of these old Legend amplifiers, is they get really noisy VRs. And when I say noisy VRs, these things are very bad. Now, I haven't powered this thing up yet. We'll experience this together. If this is like any of the other Legend amplifiers, these VRs are going to be really bad. Now, they have little holes in the top here that you can shoot some contact cleaner in to clean them out, and that usually fixes things up pretty well. So if it is noisy, I'll try that out. I'll shoot some contact cleaner in there, and hopefully it'll clean these things up. You know, in a worst case scenario, a VR would have to be replaced if it is, if it doesn't clean up or if it, stays staticky or noisy, right? So you can see we have a whole bunch of integrated circuits, or ICs. We have one here, one here, one here, and one here. And as I mentioned earlier, I'm going to show you a real common thing that techs do that just absolutely destroy these things. And I'm sure you're going to find this very amusing and very helpful. So this is, again, one of those golden nuggets. This is one of the things that you do not want to forget whenever you're working on anything that has a hybrid technology. And a lot, and I mean a lot, of the modern guitar amplifiers are a hybrid technology, so something to keep in mind. This amplifier is a very straightforward design. They've socketed all the ICs. So you can see that they're thinking, like these are just socketed, they're just pressed in, there's no restraints or to hold them down or anything like that. And you can tell that they knew back in the day that chances are some tech is going to come in here and make that mistake. They're going to come in here and they're going to pop it. So they made it very easy to get these things out. In order to get this circuit board out, it really is a pain. You got to take off all the knobs on the front. You got to undo all of the nuts here. You have to get on the other side and remove some of screws here that hold the actual circuit board down. And then, you have to move this whole thing out. It really is a pain to get these things out if you want to start changing components on this thing. And of course, one of the easiest things to destroy on these are these ICs right here. So it's very nice that they did that. They put them into sockets. Downside to that is sometimes they get noisy in their sockets as well. So it's always a good idea to remove the IC and, check the socket, spray a bit of contact cleaner on the IC pins, rock it around in the socket as you're pushing it down, and that usually makes them good to go for a long period of time. Now, I'm never really a fan of any type of hot glue, and it looks like they're using hot glue on these things to hold the components steady. You can use a non-acidic type of a silicone that will do the same job, and you can just very easily peel the stuff off. Now, mind you, hot glue is very easy to get off if you use rubbing alcohol. So 99% rubbing alcohol on a Q-tip, if you just rub it around the surface and move it around, the hot glue will just come right off. But silicone is a little bit more flexible and it doesn't end up cracking. You can see these capacitors over here. These are high voltage caps, and I'm not going to go about sticking my fingers over here right now because I don't know if these still have a charge on them. But you can see these capacitors right here, they have hot glue on them, but you can see they've separated. You see that? The actual hot glue is broken. If that was a silicone bead here, that wouldn't be broken, and they would still be held nice and tight. As you can see, these will move around under high vibration, and chances are that is what has caused these to separate like this. So you got to remember that these things are carried in mobile applications, and of course this has a speaker right underneath it, and this is capable of doing 60 watts. That is a lot of noise coming out of that speaker, and those vibrations will eventually cause any type of a glue that is hardened to crack and break. Another thing that should have been thought of here that the engineers didn't think of is they put hot glue around this capacitor and around this resistor. This is a heat generating component, and as you can see, it's melted that hot glue around the bottom here. Now, this is not the type of glue that goes conductive, so I'm not really too worried about this. In some of the later devices, some manufacturers, I won't mention any names, used a glue that was opaque that would go conductive, and you can poke your ohm meter leads directly into the glue this far apart, and you'll get an ohm reading on your meter. And basically what that does is that shorts things out after a while. I find it really interesting how they use that glue in a lot of high voltage circuits. Very, very interesting. At any rate, this is hot glue, so it isn't going to be doing that. It's just, going to crack and look ugly like it's doing in here. Now, as it was mentioned earlier, it had staticky controls, and the owner of the amp says that the speaker was somewhat intermittent. It would kind of turn on and turn off and get crackly and do all sorts of things. Well, I found this little insulating washer in the chassis, and if we take a look here, look at this. This 1/4-inch jack is just laying on the chassis. If we look at the back side here, speaker 1 and speaker 2, this is basically come right out. I wonder if this is loose. Oh, it is too. Look at that. Look at how loose these are, right? So is this one loose? No, that one's actually pretty tight. So you can tell that somebody's either been, trying different speakers or something over a long period of time, and this has all come loose. Another thing that causes these things to come loose that a lot of people don't think about, and a lot of people don't realize this as well, and this is another catch that will fry these amplifiers up. You got to be careful. This is an insulating washer. So basically the barrel of this 1/4-inch jack, so if we look here again, you can see that there's a barrel here, right? That barrel cannot touch the chassis. You can see how there's a little bit of a ridge. Let's see right here. See that little ridge right there? That ridge fits right into that hole just like that. And that holds that barrel away from the chassis. Now there's two parts to this washer, and of course this was laying in the chassis, so this is outside the chassis. I hope this is just dropped inside the actual cabinet, so I'll look for that. One thing that does happen is when these nuts on these 1/4-inch jacks vibrate loose and fall off, you know where they end up? On the speaker magnet. So I'll see if I can find that on the speaker magnet. They fall off and they just kind of get sucked onto the magnet and they're stuck somewhere around the perimeter. So I'm hoping that that's there. This is going to be, hopefully I'll be able to find that. If not, I'll just have to look through my parts bin and find another one of these insulating washers to put on this side, because there's one on each side. There's one on the inside and one on the outside, right? So this is obviously why the speaker is cutting in and out. So hopefully it hasn't damaged the output transistors or anything like that. Nothing looks like it's really baked up in here. And he said the thing did work. The speaker is obviously plugged into this. So these jacks are going to obviously need to be, look at that, how loose that is. It's going to all need to be tightened up. And I'll have to get that tightened back into the chassis before I fire this thing up. So we're going to experience this all together. We're going to go through this thing and see what kind of horrible, scratchy, staticky sounds this thing makes. And address the issues that need to be addressed. And I'm going to show you that catch that a lot of techs do that fry all of these ICs. So something to keep in mind. This is, again, that little golden nugget that I want you to hold on to, and I want you to always remember this. Lots and lots of hybrid technology amplifiers out there today, and this is such an easy thing to forget and to do. So we'll touch on that here in just a little bit. Just before we get into the repair of this amplifier, I was going to show you that reverb tank. This really is all it is. You can see we have an output side and an input side over here. This just sits in the bottom side of the chassis. Actually, this sits on a piece of cardboard and it's wrapped in a bag. And this is what creates all of that echoey special effects. A bunch of springs here. We have two little coils on each end. So one is an input and one is an output coil. As you can see, this one here is very clearly marked output. And this side is marked input. And if I just tap this, you can see how that would create the echo. So basically they're feeding a signal into this thing. And any type of vibration from the speaker and all that adds to this. So kind of a neat setup. Just before I apply power to this Legend A60 amplifier, there's a few things that you need to know if you're following along. First of all, these amplifiers have high voltage present in them. So there's high voltage available for the power transistors. So from end to end, there's about 80 volts there. And there's hundreds of volts on the vacuum tubes themselves, so there is quite a shock hazard inside this chassis. So if you haven't worked on amplifiers like this before and you're unfamiliar with this hybrid design, or basically any type of amplifier design, you should really do the research before you start working on these things. If you're uncomfortable about working on any type of an amplifier like this, do not work on it. There's enough high voltage in here to seriously hurt you. So if you're following along, you're doing so at your own risk. Please be careful. I have my audio signal generator fed to the input here. So I have it's just a little over 400 cycles running into there. All of the main controls, so the volumes, are right at 0. The rest of the controls in the reverb are at 5, and the main reverb control is at 0 itself. This is the foot switch connection here, so I have a jack into the foot switch so I can select different parts of the amplifier. Really, it's just a stereo quarter-inch jack right over here. This is running off to the speaker, and that's pretty much it. So very low-level signal running into this thing. So I have an audio signal generator with the attenuator at 0 dB, and basically the amplitude is just, a hair off of the minimum section, I guess you could say, so in the very low millivolts. So I'll turn on my isolation transformer and variac supply. It's current limited. And I didn't hear any thump on the speaker or anything like that, so let's see if this thing is working. So it looks like this little red LED is on over here. So chances are, so this is going to be, since this green light is on, this is going to be the master. So I'll turn this up just a little bit. Oh, I can already hear it. So, hear how scratchy that is? Whoa. See, there you go. This is a good example of a Legend amp right here. Listen to that. Sounds like bacon. And we can see if the reverb works. Yeah, no problems there. You could probably use a shielded lead or something like that. Let's see if I can get rid of some of that hum. A little bit. A little bit of audio line hum in there. You can hear that echo. Hopefully you can hear that. So no problems there. The reverb section is definitely working. So lots of scratchy controls, as you can see. So I'll go back to here. It's the master. So what I'm going to do here, let's just turn this down so we don't have to listen to that, is I'm going to take some of my favorite contact cleaner, and what I'm going to do is just blast it into these holes here. So I'll give it a shot into the hole, and then what I'll do is I'll move the control around. Now this is all going to be done with the amplifier off. Okay, so what I'll do here is I'll actually give you an example. So what I'll do is I'll just give this one a shot. Alright, so just like so. Now notice that I'm not touching any of the circuitry because chances are there's still a charge on these capacitors. Okay. Give it a shot like that, and then move the control around like this a whole lot. And then, after I've done this for just a little bit, I'll give it another shot again. Like so. And just move it around like this, and then I'll go on to the next one and do them all. This is the second one in, so I'll go all the way along here, and I'll do that, and we'll see if that cleans that up, and I'll save you from the tedium of watching me do all of this, so I'll be back in just a moment. I gave all the VRs a nice cleaning with a good contact cleaner, and you can hear, I'll turn up one of the main controls here, and you can hear how you can drive the front end of this into distortion. Listen to this. Now if I was to turn this up, I'd go deaf, so I'm going to turn that down. Still got a little bit here, and then I'll turn this one up. No problems there. So you can see, no more problems with noise. All the controls are nice. Just turn that down. That's the main right there. So no problems with the controls. They all cleaned up really nice. So now the next step is, let's follow the signal through this amplifier here, and I'll show you that little trick on how not to zap these ICs. Another thing that I'm going to do too is I'm going to shut the amplifier off. Actually, I'll do that right now. I'll shut the amp off, and I'll get my capacitor discharger. This into the shot here. A little bit of dust on that. Dust on that. Okay, so let's go after these capacitors over here. So the unit's been off for a bit. Let's see how much of a charge there is on here. Quite a bit, actually. Keep an eye on the little red LEDs here. Okay, these ones here. Seem like they took a real long time to discharge. Some really good capacitors. Should be replaced, but you know. These ones here hold quite the charge. If you were to slip with a screwdriver across that, there would be some mighty nasty sparks. So all the capacitors here, all the large capacitors are discharged in the chassis. Now what I'm going to do is I'm just going to remove these ICs here. So they're relatively easy to get at. So what I'll do here is, you can see that that one is looking like it's pretty wet at this point because of all the other contact cleaner floating around. You can see how easy these things come out. That capacitor's just wedged in there. Wow. From this side here, and one more from this side here, and that should probably take it out. Now you want to make sure that when you take these things out, you put them back in the correct way. There's a little IC right there. So this is a 4558. So MC4558 or whatever would be just fine. Focus on this up nice and close. Kind of hard to see the number there. So it looks like RC 4558P. I'm just eyeballing that number from over here, so hopefully that's what it is. So if you were to look up a data sheet like Motorola MC4558 or XR4558, they'd all be the same thing. At any rate, so what I want to do now is just spray some contact cleaner in that socket there. And of course, taking note of the way that the IC came out this way right here. I want to put that back into the socket, and I'm going to rock that around a little bit and press it back in. And I'm going to do that with all of these ICs here. And by doing that, if there's any type of an intermittent connection from these things or any kind of tarnishing on the pins, any kind of corrosion, it'll get rid of that and it'll make a nice solid connection back into the sockets here. Ideally, these things should be soldered onto the board, but you know, it's kind of nice to have these here because again, you come across these amplifiers all the time with blown ICs because of what I'm about to show you. We're now ready to start chasing a signal through this amplifier, and the very first place that signal goes is into the vacuum tubes. So that can easily be traced by following the coax cables over to the circuit board and then right over to the vacuum tube. So, if you recall from the Fender amplifier video, the signal goes in the grid and it's amplified on the plate. So since there's no schematics available for this, I just have the vacuum tube datasheet, and this stuff can all be found online really easy. So if we look at the pinout of the tube, so this is the tube here, and this is looking at the bottom of the tube. So this is pin number 1. So if we look over here, we can see the gap over here. So technically, this would be like this. And the way you count the pins is exactly the same way as we're looking at the bottom side of the socket here. You count clockwise from the index, which is the opening here. So if we look here, we can see pin 1. If we follow the line, it brings us right up to the plate. Or if you want to look at the legend, it just says pin 1 to plate. If you follow the line from pin number 2 on the vacuum tube, it goes into the dotted line. That's the grid. So the signal goes in pin 2 and it's amplified on the plate, which is pin number 1. So we should see a small signal on 2 and a very large signal on 1. And that'll tell us that this stage is amplifying. It really is just that simple. You don't need any type of a special oscilloscope to do this at all. You don't need any on-screen display or anything. All you're doing is you're looking for clean amplitude. So here we go. So this is the input here. So that's the signal coming out of my signal generator. So now, if we want to see if this vacuum tube is amplifying, we just have to go to pin number 1, the plate. And the amplitude should go right off the screen. So I'm going to have to turn down the volts per division. My scope right now is AC coupled. And when you have your scope AC coupled, it'll keep the signal right in the center of the screen. If you DC couple your oscilloscope, it's going to show a DC level. So you can see that there's boxes on the screen. So that would be 1 volt per division or 2 volts per division. So per division is per box. So just say these are 1 volt per box. If this is DC coupled, and say I was to touch the probe to a 2 volt source, if it's a volt per division, it would be up at that second box. So the line is going to go up. Now, you got to understand with a vacuum tube, when you're looking at the plate, you have a high DC voltage there, and you also have an AC signal there. So if you want to see the AC signal without having that DC voltage present on the screen, without having the scope trying to display that voltage, you want to have your scope AC coupled. If you had this DC coupled and I touched the plate, since there's high voltage on there, this is just going to shoot off the screen and it's not going to come back until I turn my volts per division to a point to where it's going to fall within the boxes or the graticule on the screen here. So that's the difference between DC and AC coupling. So in short, DC is going to show you the DC level. So technically you could even use your scope as a voltmeter. All right, so if it's DC coupled, the line will move up for every volt, whereas AC coupled will keep the AC signal in the center of the screen all the time. So that was a question from a patron. So hopefully that helps you out. If you have any more questions about that, please feel free to post your questions below and I'll try to address them. So here we go. So now we'll go to the plate. So we should have a really big signal here. Look at that. It's right off the screen. So I'm going to have to adjust this. All right, to 10 volts per division. So you can see that we have that on there. So now if I go to the grid again, you're going to see that, see how low that signal is there? And how large that signal is there. And it's just that easy to follow the signal through the amplifier. Technically, we've already gone one stage. So if we want to go over to the other side, we can see here, if we look onto this side here, so there's 2 amplifiers inside this one tube. So there's 2 triodes. So you can kind of look at this like being, there's 2 N-channel FETs inside this one glass bulb. So the grid would be the gate, the drain would be the plate, and the source would be the cathode. And that's how it works. So gate, drain, source. And it'd be the same on this side. Gate, drain, and source. So what we want to do is we want to see in the grid and out the plate. This is really easy to follow. You can see pin number 7 looks in the grid. It comes into the grid here, and we can see that it runs out of the plate. So pin number 7 is going to be, so go 9, 8, 7. So if we go to pin number 7, you can see that there's very little signal there, and that's because this is turned way up. So I'll turn this way down again, and as you can see, there's our signal present right there. Okay, so again, in the grid. Now if I go to the plate, what am I going to see? Well, I'm going to see a really large signal. We're going to see the amplitude shoot right off the screen again, right? So we'll go to pin number 6, which is just 1 over. Look at that, right off the screen again. Right there. And as you can see, we've just verified that that tube is amplifying, just that simple. We didn't need any of this on-screen display or anything like that. All we're doing is looking for clean amplitude, and we want to make sure that it's amplifying. It's just that simple. You can use an oscilloscope from 1940, from 1930 to do this, no problems whatsoever. Most of those scopes are all AC coupled anyways. So that makes things nice and easy. Now here is the catch, okay? Here is what pops these ICs. I want you to remember this because this is very important when you have your scope AC coupled. You can see that I have my oscilloscope probe on that pin right now. So what I'm going to do is I'm going to grab my voltmeter right here. Okay, I'll just put this here. Hopefully there's no glare on the screen. It looks like it'll be okay. All right, and I'll just clip this to the chassis. Do I have the clip? I do. Okay, so I'm just going to ground the probe to the chassis here. So this is my voltmeter. So if I touch the plate, so this is where the oscilloscope is coupled to right now. So if I touch the plate, there's 182 volts there. Okay, there's 182 volts on that end of the oscilloscope probe. Now watch what happens when I take this probe off and touch it to the chassis. Watch the screen on the scope. I'm touching it to the chassis. You see how that shot off the screen there for a second? Well, why is that? Why did that shoot off the screen like that? Well, because there's a cap holding charge. So if I was to take this off of this pin right here, all right, so I'll clip it back onto the plate. You can see that's present there. If I was to take this off of that pin and touch one of the ICs here, I would fry that IC immediately. So what I'm going to do here is I'll go to the peak setting of my scope, okay? So this is going to be really sensitive. You can see it just bumping up shortly. So this isn't going to be incredibly fast. Like this is not a super insanely fast meter, but we'll get an idea of how many volts will be on here. Okay, so I'm just going to touch the probe to my voltmeter now, and this will just quickly record it. Okay, so that was 15 volts there. Now this is an auto ranging, so if I change this, let's go to 500 volts, and we'll start that again. Okay, so I'll clip this back on here, so we got our nice reading, and I'll go back to the probe lead. This will be faster now. Yeah, 54 volts. The moment I touched this probe here, that recorded 54 volts. Now you got to keep in mind that there's a bit of response time in there. Chances are that was right up at the level that was at. So even with the response time, it still measured 54 volts from this probe to ground. So as you can see, it's storing a charge. You have to be careful because some probes and some oscilloscopes will do that. Now, this is a real common problem with frying these ICs. You go directly from this right over here, so you clip it onto the signal right here like that, and now this is charged up. So what you want to do with your probe lead, just to be safe, this is such a simple thing to do, is just take your probe lead and touch it to the chassis, just like so. And then that way you're safe. You don't have to worry about this zapping the IC, because if you go from a vacuum tube to an IC, that would 100% destroy that 4558. Any lead I put that on would just absolutely fry that 4558 up. So something to keep in mind, something that so many techs overlook. Now, if we wanted to follow this signal into the first 4558, here is the trick for this. Very simple. This is just an OpAmp. All right, there's two of them inside this package. Okay, so you can see that we have a positive and negative input, and the output is on pin 1. So whenever you're dealing with an amplifier like this, these op-amps are either going to be wired to give you gain, or it will be unity gain, so it'll be configured as some form of a buffer to create some drive. So what you would do is you would probe the output and see if you see a signal there. If you see a signal there, chances are the op-amp is okay. So what we'll do is we'll take a look at pin 1, because that's the output. So if you remember, in an op-amp, you look at the end of the arrow. So the arrow points to the output. So we have an output on pin 1 and an output on pin 7. And this IC is configured like this in the chassis. All right, so that's pin 1, and then pin 7 will be over there. So I got to turn the sensitivity of this, because we're dealing with a solid state device. I'll just turn the sensitivity up. Again, I'm going to make sure that my scope lead is discharged. Do you see that, how it went up there? I'm going to be very, very careful. So let's just probe pin 1. Look at that. So we have signal on pin 1. Let's see if the volume changes this. Look at that. The master changes that, so we can tell that the master, this is after the master. And if we go over here, I got to hold this very steady on this because this probe doesn't have a... Put this through here, just like so. There it is. And we can see the signal on pin 7. No problems, just that easy. That's how easy it is to verify the stages in here. And you just go along from 4, 5, 5, 8 until you, if you're in the amplification chain, there's going to be some over here for the reverb tank as well, but you would get signal on those ICs as well. All you really need to do is just check for the output, pin 1 and pin 7. Now, if you don't have any output on pin 1, you would check pin 2 and pin 3. If there is a signal on pin 2 or pin 3 and there is no signal on pin 1, so say you have a pretty decent amplitude that like we just saw on here on pin 2 or pin 3 and there's nothing on pin 1, instantly the op-amp is suspect. Just that simple. Again, checking pin 7, if there's no signal on pin 7, all you do is you look for a signal on pin 6 or pin 5, one of the inputs. If you find a signal here and no signal here, you know that the op-amp is suspect. And it's just that simple. Really is. So you can just go along from stage to stage and check all the op-amps that way. So all you need to do is just get yourself a datasheet, and the stuff is available online all over the place. Datasheet archives and all these places, they all have these datasheets that you can look up. And this one here is for the 4558. That could be MC 4558, XR 4558. Like there's just so many 4558s out there. 4558 is a really common op-amp, just about as common as dirt. So if one of these things was to ever fry up, you could very, very easily find these at any parts house. So very easy component to replace. And that's how easy it is to troubleshoot the signal path in one of these amplifiers. And of course the signal is going to end up right over here. I'm sure we're going to have some amplitude on the output here. It's going to end up right over here. And that's the output. This runs off to the speaker. You see that? Look at how quickly that moves up. I'll just give this a little bit of... there we go. Look at that. No problems whatsoever. As you can see, the control's nice and clean. No scratchiness there or anything. Lots of signal at the output. If I was to attach the speaker, I have this attached to a dummy load right now, so I'll just make sure that this is down. And you can see that. So that's me scratching this over here. I don't know if you can see that. That's me scratching the terminal on the thing, the VR. You can see that. That's me doing that. So the VRs are nice and clean. This is just rubbing it on the 1/4-inch jack. That's what's making that scratching noise. At any rate, you can see just how easy this is to troubleshoot. And this here runs right off to the speaker. So this little purple wire, kind of a pinkish purple wire, runs over to here. And then there's a trace that runs over to here. And then it runs off to this purple wire. Now here is something that is very interesting on this amplifier. This switch right over here, let's move this scope out of the way. This switch right here is a standby switch. You know what the standby switch does in this amplifier? It doesn't switch any high voltage off. It doesn't do anything. You know what it does? It disconnects the speaker. So all of those guys out there that think that, running an amplifier, especially one of these particular amplifiers, without any load or without any speaker, will damage it. This one here, when you click it into standby, purposely disconnects the speaker from the output transistors. So there's your answer with running one of these amplifiers without a load. Completely fine in this situation. You just click this off. Here, I'll give you an example. I'll just move this out of the way, take the load off, turn this back up here a little bit. Whoa, loud. There you go. That just disconnected the speaker. Even some echo in there as well. So there you have it. Solid state amplifier, no load. In this case, not a big deal. I talked about the no load situation as well in the Fender, the vacuum tube amplifier one as well. And there was a bunch of questions there saying, well, why would you even bother running it without a load? Well, if you're looking for low level hum, or if you're looking for noise, when you hook a load across it, what it does is it basically reduces the sensitivity that you can read on your oscilloscope because you're hooking a load across the speaker output. If you eliminate that load on the speaker output, you can look for very, very low level hum and have no problems finding it that way. And that's the reason that you want to run a vacuum tube amplifier with no load. That's just one of the test conditions. Again, if you are using a vacuum tube amplifier and you're going to be putting out any substantial signal, yes, you want it into a load. But for looking for small level, noises and signals and scratchiness and things like that on the output, it's absolutely fine to run a vacuum tube amplifier without a load. Again, just make sure that the volume is very, very low. I hope you're enjoying me sharing this Patreon Super Troubleshooter series with all of you. If you are enjoying these videos, you can let me know by giving me a big thumbs up, or you can leave a comment down below in the comments section as well. The whole idea of this Patreon series is to share my skill set with all of you. So this goes well beyond troubleshooting on Patreon. I'm sharing my designs and even inventions up there as well. There's over 50 videos up on Patreon right now, and the list is growing. So if you're interested in having my skill set or learning about my skill set, you're definitely going to want to check out my Patreon page. I'll put the link just below in the description, and I'll also pin the link right at the top of the comments section as well. So if you click on the link, it'll take you right to Patreon. When you do get to Patreon, and if you do sign up, another tab will appear just below the picture of my lab. It's called the community section. In that community section, you can ask other community members about your projects. You can even post pictures and all that kind of stuff as well. So you can share the projects that you're working on right now and get some ideas from the other members. There's a lot of very, very nice people up there, and a lot of them have a very incredible skill set. So don't miss out. Check it out. So until next time, take care. Bye for now.